Welcome back, everyone. Today, we are going to actually be revisiting the concept of linear combinations, but also looking at an introduction to span of these linear combinations. So let's get started. So let's get the title so we can actually remember which page is which. Linear I'm just going to abbreviate this. Combs and intro to span. Okay, so let's get started. So what do you recall a linear combination being? Well, basically it's some vector, let's say some vector A times some constant c plus some other vector b, and that's equal to some vector c, right? So this is a basic linear combination, right? We can express this in a set. We can express this, just algebraically. But yeah, this is just a basic representation of span, or linear combinations. But whenever we're looking at span, you actually want to fully understand the entirety of what this of all the values of c and all the values of c and basically what that spans. Meaning, for example, I don't want to get too deep actually here, so I'm actually going to set vector A equal to something. So vector A can be equal to 2, 3, I guess, and vector B can be equal to 0, 6. Okay. So now let's write this in here. So A times some constant C1 plus B C, should be C2, my bad, equals some vector C. Okay, so this is the basic concept, right? So let's set, why don't we set C1, say C1 equal to 3 and C2 equal to, I don't know, 1/2. Let's try that. So what would that equal? Basically, it's just, we can cross this out with 3, cross this out with 1/2, and it's just scalar multiplication, remember? And then that's just equal to 6, 9, plus obviously 0 and 3. And that is equal to, so let's just add the terms like so, 6 and 12. So this is our combination of these two vectors where C1 is equal to 3 and C2 is equal to 1/2. So let's basically define what we're seeing here. So actually, why don't we define span, just so you can get a look at things. And by the way, we're looking at all vectors, all vectors, vector v's that are all members of Rn. Right, so any dimensions of space. We're not specifically looking at coordinate points because we're not worried about graphing anything today. I have some pretty messy handwriting at the moment. So let's get a visual representation of span first of all. So let's look at this. So let's take our two coordinates A and B, let's plot them. A, it's 2, 3, so that can be A, and B, 0, 6. My bad, that's incorrect. It's like that, 0, 6. So just ignore that line there. So essentially what we're looking at is the linear combination of all the possibilities that we can add these guys here. So basically, if you look at it well, we can obviously scale this by anything we want, right? Anything we want, we can multiply by negative scale factors. We can do anything we want with these, and we can add them as well. So we can do things like this, we can do things like that, we can do things like that. We can also go up, of course, that's its regular position. We can scale it down infinitesimally, as much as we want. So we're starting to see that actually this spans the entirety of this R2 coordinate plane. These are both of these vectors are in R2, of course. So what you would say is basically the computation that you would use, or function, you would use a span. So the span of these vectors A and B is actually R2. Why? Because, well, we can make any vector C. Let's say the sum of all these vectors is of these two, the combinations of these two vectors is C. So the C could be any vector in R2, right? Any combination of, whatever combination of this, well, you can just name any C, and you can find some combination of these two vectors, and you'll be able to get C. So this is what this means. And I'm going to formally define span. So the span of some vectors, I guess, v1, v2, all the way down to vn is actually equal to, let's see, so vector 1 plus, vector 1 times c1 plus vector 2 times c2, all the way down to vector n times cn, such that ci is a member of the real val of the reals, for which, and these can be scaled by anything, right? So c can literally be anything from 1 to n, or yeah, so from 1 to infinity, but I don't think I would like to graph it in such an interval fashion, so I'll just from 1 to n. Yeah, that makes sense, because from 1 all the way down to the value here. And that is our set. So that's the formal definition of span, right? So let's look at some more examples of span. I can just turn this over, actually. So let's say should we stick to the same vectors, or let's look at some other vectors. So vector x, set that equal to 6, -4. Set vector b equal to 5, -8. Whether we're going to be really using them heavily is the question, but we'll just have them there just in case. So let's say we want to actually multiply both of these vectors by 0, and hopefully you'll instantly know what that is. Let's say our scale factor is 0, so 0 multiplied by x, our vector x, plus 0 multiplied by our vector b. What is that equal to? Well, that's just actually equal to the 0 vector, which can be signified by bolded 0, because all the terms will be 0 in that vector. It's a two-dimensional 0 vector. And yeah, I didn't expect us to use that very much. What else can we do? And so again, actually, this 0 is actually the span of the 0 vector here, right? So how do I explain this? So let's say we have the span of our 0 vector is obviously equal to just 0, right? Because it only stays at the origin, it doesn't go anywhere else. But also you might be thinking, if we have any combination of two vectors, if we disregard this combination here, where a C1 and C2 are equal to each other, then you might think that all the rest are, all the rest can span the entirety of R2, or any dimension of space. Well, actually, that's not true. So let's take a look at two vectors which are collinear. Take vector C, -6, -4. Take vector D. They're just variables picked at random. 6, 4. We can see this is just the opposite sign of this one, right? And we can easily, I'm not going to graph the points, but we can easily see that it's something like this, right? On both sides, and these vectors are equivalent magnitude, but just opposite directional vectors, right? Well, the problem with this is that we can scale them by anything here, right? So C1 times vector C plus D times vector C2. Right, we can scale them by anything, we can add them in any way. But what we can see is that since they're collinear and all their solutions will only be graphed by one single line. So in essence, you can scale them, right? But when you add them, they either cancel each other out or just make the line longer, or make it shorter, depending on the magnitude, right? So actually, you can think of this as just some constant C times a single, because this is actually just equivalent to some constant C1 times some vector A, right? If you have some vector, for example, if this is vector A, and again, you can't manipulate these two vectors so that it gets this. It's not possible. This is some separate vector A, and any constant times this will get it to anywhere along this line that it's on, right? Along its x slope, right? So that's the intuition of that, right? So hopefully that makes sense. So what else could we cover? Let's see. Is there anything else I could cover? There's also so essentially what I'm saying, if you still don't believe me that you can actually receive any value, here's an actually this is a different way of solving, since in the past we actually used the method of using matrices to solve, or basically in the same way as solving systems of equations. You can actually solve systems of equations. You can actually solve it's hard to explain, but let's say you have some x1 times some vector a1 plus some vector y1 times vector b, and that is equal to some vector c, and these are defined, but we just not worried about defining them right now. And basically you can solve for these two values. If we are aware of a, b, and c, it's essentially just like solving a system of equations, right? You can solve it in the same fashion. And that's what we looked at last time, but there's another way of solving it algebraically, and we can take a look at that. I'm actually unsure if we have enough time. Basically, if we select a vector A, for example, 4, 6, -4, 6, and vector B to be 5, 8. Okay. I'm actually running low on time, so I'm going to continue this in the following video, which would be probably in about 10 minutes. So hopefully you enjoyed. I'll see you in the next video following very soon.